Welcome to the lesson video for the k-nearest neighbors predictive model. K-nearest neighbors is a method for building predictive models for both classification and regression. In this first example, we're going to walk through the k-nearest neighbors method for building classification models. So on the left-hand side of the screen here, we have a pair of axes, which are labeled feature 1 and feature 2. And on these axes, we have some toy demonstration data plotted. And the way the k-nearest neighbors method works, it's very conceptual, fairly easy to understand from a simple example. Suppose I have a new data point, and I'm going to compare this new data point to its k nearest neighbors, where k is the number of neighbors. So if k were 3 in this case, I would take this new data point and look at its 3 nearest neighbors. So there's the 3 nearest neighbors, and I can create a name for all those neighbors. We call it n naught, just the neighborhood. So we look at these 3 nearest neighbors, and I'm going to predict this new class label for this new data point is going to be the class that's most abundant in this neighborhood. And so here's the way we write that for prediction. So in my toy case, I'm going to label this new data point blue because all 3 of its 3 nearest neighbors are blue. If my new data point were right here, I would look at its 3 nearest neighbors, and I see it has 2 orange neighbors and 1 blue neighbor. And so this data point here is going to get labeled orange. We can also compute not just a prediction for what the value should be or the class label should be, but a probability for the different class labels. And so here's the formula for the probability. And so the way we read this is P for probability. This is the probability that y is equal to class j. So this is probability that the class assignment for this new data point is equal to j, given that the x value for this new data point is equal to x naught. So we're looking at some new data point x naught, and we're going to compute the probability that we have this class label. And so here's the formula. The formula is very simple. We just look at the neighborhood of this new data point, and the probability is going to be the number of points that are in that neighborhood divided by that are in that neighborhood and are in class j, and divide that by the total number of points that are in that neighborhood. There's a different way to write this formula. This is the textbook way to write the formula. It's more in the flavor of statistics and formal writing, less conceptual than the formula that we provided above here. So we have two formulas. This first one, which is more conceptual, and the second formula, which is the textbook way to write this. And so you'll look, when you read the textbook, you'll walk through that different components of that second formula. Now, k-nearest neighbors can also be used for regression. And so on the left-hand side here, I have some, again, toy data. And what I have is a number of data points. They don't have class labels assigned to them, which we often show with colors. In this case, they have numbers assigned to them. So we're doing a regression problem. We're trying to predict y values where y values are continuous valued numbers. And so let's pick a new data point. We'll insert a new data point into our field, and we want to predict what should the y value be that we're going to assign to this new data point. And so we look at, in this case, we're going to do 3 nearest neighbors again. So those are the 3 nearest neighbors. Again, this set of points that are its n nearest neighbors, we call that neighborhood n naught. And so the prediction for this new data point, it's going to be the average value of all the y values for points in the neighborhood of n naught. So in this case, we take the average of 2.2 and 3.5 and 1.7, and we get 2.46 or so, which we'll round the 2.5 for the sake of keeping consistent significant digits with the other data that's provided here. And so that's how we do prediction for regression on k-nearest neighbors. There's a couple of challenges that come up with k-nearest neighbors. Anytime you come up with a prediction algorithm, you want to understand what are its pros and cons, and what do you need to do to implement it well. So for k-nearest neighbors, we have to choose the value for k. In the previous 2 examples, I used a value of k of 3, but that may not always be the best way. So what we do to pick the value of k is we'll compute the k-nearest neighbors algorithm for different values of K on the training data, and then compute the accuracy on the test data or compute the error on the test data, and choose K that gives us the minimum error on the test data. Another challenge, we often have different feature variables that have different units. So what would I do if one of my features were in distance of kilometers and the other feature were in the distance of seconds? Right, so these might have wildly different scales, and one might dominate the computation of the distances. So often what we do when we have features that are in different scales and we want to try to compute K nearest neighbors is we'll scale each feature value so that it has a range of 0 to 1, or maybe make them each have a mean of 0 and a standard deviation of 1, and use some sort of normalization method. K nearest neighbors can struggle for certain on data where the values or the distributions on the different features are different. Here's a figure from your textbook showing a set of 2-class data for classification, and so shown on the right-hand side, features X1 and X2. There's 2 classes, one class labeled orange, one class labeled blue. And this is a distribution that has a nonlinear separation. The optimal separation, shown in purple here, this is called the Bayes decision boundary. It's what you would get if you used the Bayes classifier, which is if you knew everything there was to know about this data, and the author knew everything there was because he created the data from some random distributions that were known, you can compute what's called the Bayes classifier and look at the Bayes decision boundary, and that's the optimal boundary and the optimal classifier. The author shows in this figure that when K is 10, we see that we get a pretty good decision boundary, and visually it would look good to us. And if we compare it, if we happen to know the Bayes decision boundary, we can compare it and say, hey, this is pretty close to the Bayes decision boundary. We almost never actually know the Bayes decision boundary, so having it here in this picture is more for means of comparison, so we can evaluate performance on this test data. Here's a couple other figures where we have plots of the data and then decision boundaries using K equals 1 on the left and K equals 100 in the center. And we see when you use K equals 100, our decision boundary flattens out. It loses the ability to contour to the data. When K equals 1, it's contouring far too much to the data. Right? It's looking at only the 1 nearest neighbors for each data point, which are themselves, and it doesn't give us performance that's going to generalize well. On the plot on the right-hand side of this figure, we have the 1 over K is on the horizontal axis and the error rate on the vertical axis. And what we see here plotted are the training errors in the teal. Right, so those are the training errors. So that's when you train in your data and then you apply the algorithm back to the data that you trained it on. We don't care very much about that. What we really care about are the test errors, which are shown in orange. And you see when we use K equals 1, that's this, we don't get very good accuracy. And when we use K equals 100, again, out here, we're not getting good accuracy. The sweet spot for this algorithm is really anywhere in this range, kind of centered around 1 over K being 0.1 or K being 10, which is what we saw on this slide just previously, that when K equals 10, we get a pretty good looking decision boundary. So that was found, if we see on this right-hand slide where we circled in red, by finding where the minimum value is for the test errors. And often you'll get sort of a range of minimum values, and you want to generally pick something that's towards the center of that range. So let's look at some other data. So this is a different set of data. This is data that you're going to use in your quiz. And what we have here is a web page interface, and there's options to select your data set. So there's 3 different data sets that you'll be choosing in your quiz, and this will be opened up in your interactive part of your quiz. So the first data set is called Fisher's Iris All Features. So we've talked about Fisher's Iris data set. There's 4 measurements that Fisher made for each iris flower, and so in that data set you'll have access to all 4. This data set we're looking at now, it's bold on the button, so it's telling us this is the one that's selected. This is Fisher's iris dataset, 2 features. And then we can select either the training data or test data. Right now we have training data selected, and there's 2 selections for the boundary type, and the boundary type is the background on this right-hand side, decision boundary or probability boundary. So what we have here plotted, very similar to the figures we looked on the textbook. On the right-hand side, we have a scatter plot of the data, and then colored regions telling us where our classification algorithm is designating the regions for the 3 different classes. On the left-hand side, we have a plot of the error rate for the test data, that's shown in red, and the error rate for the training data, that's shown in blue. And on the bottom, we have a slider where we can select different values for K and find the effect on these error rates. So looking at the different plot boundary types, this selects the probability boundary. And so as we pick K, you can see how this affects the probability distributions that are estimated from K nearest neighbors for different values of K. We're more concerned with the decision boundary, and really that's what you're going to be using for this set of interactives. So let's start with K equals 1. K equals 1 with K nearest neighbors will always give you very good performance. We look at our training data, we often expect this to be 0. It's slightly above 0, and we can see the reason why we have one data point here that seems to be in the blue class, but then the same set of values also give you a data point that's in the green class. So one of those is going to get labeled wrong. When we look at this scatter plot and the decision boundary, we see it seems to be contouring around things that we expect are probably not well represented in the data. And we look at the training data, error rate's very low, but the test data error rate's quite high. And so that tells us we're overtraining. We can plot the test data on the right-hand side, and we see a lot of those contours that were present in the training data are not representative of the general data that we see in the test data. So we see the X's represent misclassified, mislabeled data points. As we increase K, we find that our training data error goes up a little bit. Our test data error has maybe gone down a little bit. And then somewhere in this range, we have our test data error that's gotten its lowest. And if you look at our decision boundaries, they look fairly reasonable for this data. And then as we increase data K too high, we get test data that starts to rise again in its error. So if we're trying to pick K, and this is often, we use these sorts of plots to pick K, it's often the choice is, how do you choose your K? In this case, we'd choose K to get our test data error rate in its lowest, so K would be somewhere in this range. And so in your interactives, as part of your online content, you're going to interact with a web page that looks very much like the one we're looking at. And for each of these different data sets, you're going to have to select a K value that gives you a good error rate. And you'll want to select it by looking at the error rate in the test data, but also considering how this plot looks on the training data versus the test data. So comparing K nearest neighbors to linear regression, and here we're talking really about the regression settings. This is K nearest neighbors regression versus linear regression. There's a couple of things we can look at when we're comparing these. First thing to look at is the assumptions that are made on the data. So the assumptions that are made on this relationship between the outputs and the inputs in our data. Linear regression assumes that this relationship is linear. K nearest neighbors puts no assumptions on this function. So if your relationship is really linear, you'd expect linear regression to do better because it has that assumption built in. If it's not linear, you'd expect K nearest neighbors to do better. Impact of the dimension of the data. Dimension here means the number of variables that we have in our predictors, or the number of features. Linear regression will need what I vaguely would term a moderate amount of training data. K nearest neighbors needs a significant amount of training data as it dimensions increases. And in fact, we know that the number of desired training samples will grow exponentially with the number of predictor variables. This has to do with what's called the cursive dimensionality. a cube or an n-dimensional cube with side L, the volume of that cube will grow exponentially with the number of dimensions. And so the number of data points you need to fill that volume or to map it out will grow exponentially. In terms of variance and bias, linear regression generally has low variance but high bias. Low variance, it doesn't have a lot of flexibility to learn certain little contours, and high bias, it assumes that you have a linear regression, so there's a potential for high bias errors if that linear assumption is not met. K-nearest neighbors regression, on the other hand, has a high variance and a low bias. And these really, K-nearest neighbors regression, linear regression, are sort of the two extremes in terms of this bias variance trade-off. That ends our slide. Thank you very much.